In this video, we will demonstrate the effect of variability on system performance by modeling a queuing system both deterministically and stochastically. The context for this problem is xfab, a leading foundry for analog and mixed-signal semiconductor manufacturing.
Hi, I'm Lloyd Wetzel. I'm the president and CEO of xfab Texas Incorporated. xfab Texas is one of a group of locations that is known as xfab Silicon Foundries, and we have locations around the globe in Malaysia, Dresden, Germany, Erfurt, Germany, and our other location is here in Lubbock, Texas. xfab is an analog-oriented facility. We are not playing in the digital realm and not trying to compete down at line widths of 30 nanometers. We're now working in a realm that's from 0.5 to 1 micron here in Lubbock, Texas, and at 0.13 and above in some of our other facilities. We are an automotive-focused organization as well. About 55% of the business we have here in Lubbock is automotive-oriented. Those parts go into things such as airbag controllers, navigation systems, window controllers, engine monitoring components, etc. within the car. So we typically run our manufacturing in lot sizes that contain 25 6-inch wafers. And those lots run through, in a typical process, about 300 steps to complete the integrated circuit. And at any given time, we'll have as many as 100 different process routings that are running inside the factory and thousands of wafers of inventory. The process flow at xfab Texas is what I refer to as a repetitive flow. And by that I mean that the material will flow through specific types of equipment multiple times while we're creating the device. So it may go through a certain piece of equipment as many as 25 times in creating that device. It may go through other pieces of equipment within the line only a single time. A common issue in wafer fabs today is that the capacity is difficult to calculate because static modeling, which is typically used, does not take into account what the variability is in the arrival time of material and the queue time of material and in the real process time of material. So it's frustrating for management in semiconductor companies not to know what the real capacity is because there's a large investment in equipment to be able to run the processes, and then not what your true return on investment will be is very frustrating. Dynamic capacity models can be created, however, they take a lot of time and effort, and they also take a lot of effort to maintain the model even after it's been established, because every time you make a change in the process flow or in the equipment, you have to then go update the model. Also, validating that model is very difficult. It may take 6 to 12 months of real production to actually validate a dynamic model. And so they're not used very often because of the effort it takes to install, validate, and then maintain on an ongoing basis is very costly. A compromise is currently being seen as the best solution for an operation such as ours is to use stochastic modeling, where you have less time than dynamic to build the model, but you have much higher accuracy than you have in a static model. So it's really seen as the best of both worlds. You can improve the accuracy of your predictions, you can take into account the variability in the process and the timing in the process, but not require 2 or 3 people to maintain that model consistently as you run it. So I personally have been attempting to try to understand what is the real difference in the accuracy of the different models, what is the cost difference, and then I can calculate what is the real value of each individual model to our company.
Okay, this is I'm Marcus Borhani. I'm one of the project managers here at xfab Texas. We are looking at our clean room area. This is our photolithography area, which basically where we print the patterns on the wafers. The reason for the yellow light, we have material that they are photosensitive to UV light, and that's the reason for the yellow light. At this process step, what we do, we take the wafers, they have photoresist on them. We expose it, the pattern. A typical device that we build here, they're CMOS or bi-CMOS devices. They could have between 15 to 20 layers of masks, and they go from this area to the next area, which is actually the etch process area, where the patterns define where we want to etch out here in the steppers. This area is our plasma area. The plasma area is a dry etch processing. Basically, the wafers coming from the photolithography area have the photoresist on it, but there are films that they could be oxide, methyl, polysilicon, nitride, that we actually introduce gases into the plasma chamber, and the film is actually etched in the machine. These processes over here, the plasma is what we call mostly a single wafer processing. So that means the wafers are etched and processed one wafer at a time. And depending on the film chemistry, various gases introduced in the plasma environment, and the films are etched in that area. Okay, this is our diffusion area. The diffusion area is a very high temperature processing, where actually the wafers see temperature ranging from 400 degrees C all the way up to 11 degrees C. What the process is actually the dopants are driven into the silicon, forming the junction of a transistor or a diode, or actually a films is grown at the high temperature. Behind me, if you look at the one furnace that has a red color on it, that is a furnace that is at the very high temperature processing. The wafers are loaded into the furnace in the quartz glass for withstanding a very high temperature processing.
The hypothesized performance of the production system when modeled deterministically, or statically as referred to by Mr. Wenzel, does not match up with observed performance. This is due to variability in both the inner arrival time of parts and service time of machines, yet such variability may be captured by a stochastic model as an alternative to a deterministic one. To illustrate this, consider a basic server queue where parts arrive singly and are serviced one at a time. The average number of job arrivals to the queue is 3 per hour. The server takes 20 minutes to service a job on average, and parts arriving to an empty queue are immediately placed in service. If it is assumed that these averages are deterministic or static values for the arrival and service times, then it follows that a queue would never form as the server would finish processing the preceding job before the next job arrives as shown here. That is, the deterministic model would indicate that the server would sit idle for 5 minutes between jobs and then be available to immediately start an arriving job. Hence, it follows that the expected queue length and expected waiting time in the queue are both equal to 0. As an alternative, a stochastic model allows for variability in the arrival of parts and times it takes to service those parts, which implies that a probability distribution is used to describe characteristics of the system. In this queuing example, assume that these distributions are the Poisson and exponential for arrivals and services. In this problem, we want to compare the queuing measures for the expected length of queue and the expected waiting time in queue between the deterministic and stochastic model. For the stochastic queuing model, let x of t be a random variable that denotes the number of parts either in service or waiting in the queue at time t. It follows that a collection of these random variables over the time t forms a continuous time Markov chain since the arrivals are Poisson distributed and services are exponentially distributed, and as such, state transitions possess the Markov property. Letting lambda and mu denotes the parameters of the arrival and service distributions respectively. The state transition diagram for x of t is given by the following. And the generator matrix is given as follows. The limiting probabilities of this system may be found by setting the Kolmogorov equation set equal to 0, which may be subsequently shown to have a repeating structure of the following. From the boundary condition that the probabilities must sum to 1, the measures of the expected length of the queue is given by the following. And the expected waiting time in the queue through Little's law is as follows.